Tim sort. Tim sort is a hybrid sorting algorithm that is used as the default sorting algorithm in Python's sort function, Python's sorted function, as well as Java's array.sort function. If timsort is used as the default in both Python as well as Java, that means there is something special with timsort. And that something is that timsort works excellently in real world datasets. So whenever you give real world datasets, timsort performs really well. The next question is, why is timsort performing so well in real world datasets? And secondly, what is the procedure followed in timsort in order to sort dataset? Let us understand both these points. So the first question is, why is timsort working so well in real world datasets? So for this, we have to first understand how is timsort called as a hybrid sorting algorithm. It is called a hybrid sorting algorithm because it uses two different sorting techniques. One is merge sort and the other one is insertion sort. So timsort uses a mix of merge sort as well as insertion sort. At this point, you may have a doubt in your mind. That is, insertion sort is having a worst case time complexity of order of n square, which is not so good. Merge sort, you know, it is having a good time complexity order of n log n, which is quite good. But what are you getting when you mix insertion sort into merge sort? This is the question. So the reason is, insertion sort, it has a speciality. The speciality is that insertion sort is really effective whenever you have small data sets, or if your data set is already in almost sorted order. In either of these cases, insertion sort is really helpful. So in case of timsort, what we will do is, one, we are going to have some conditions by which our data will be almost sorted. And the second thing, we'll be working on small pieces of our actual data set, which means it makes a lot of sense to use insertion sort in those places. And finally, once you get all those small pieces sorted, that is where merge sort is coming to play. And one more thing, this is not the normal merge sort that you saw in the previous lectures. This is going to be something special, a modified form of merge sort, which is even more efficient. So first thing, how is this insertion sort going to work? In our shell sort lecture, we discussed that naturally occurring data, generally any random data set, has a speciality. That is, there will be some natural order in that data set. If you take any random array, let us say some unsorted array, it won't be totally unsorted. The point is, there will be some small runs in that data set which are sorted. So maybe if you take a very large array, consider this is a very large array, there will be some parts of that array which is already sorted in ascending order. Again, you will find some portion which is already sorted in ascending order. So this is naturally occurring in all data sets, because think, if none of the two elements in this array are in sorted order, that means the complete array is in reverse sorted order. And that means if you simply reverse all the elements, you will get a sorted data set. So it is always true that you will always have certain parts of your data that are already sorted. So here we'll call those parts as runs. Okay. So this may be a group of elements which are already in ascendingly sorted order. So considering that we want to sort in ascending order only. So these are the steps to be followed. First thing, whenever you get a new data set, an array, let us say, to be sorted using timsort, you will identify all the runs in the data set. By run, we already said it is a ordered part of the data. So here we want to divide complete array into different runs, which means surely you won't get complete array as different sorted parts. There will be parts which are not sorted. So whenever you identify these runs, First thing, try to identify naturally occurring runs. This is the first thing. Second thing, it may so happen that there will be some runs which are in descending order. If you can find runs in ascending order, then obviously there will be some runs which are in descending order as well. Take those runs, simply reverse them and make them in ascending order. And the third thing, this is important, wherever you are not able to satisfy minimum run length, use insertion sort in order to make those runs as minimum run length. What is minimum length? Generally, we use a minimum length constraint which would generally be between 32 and 64. So your minimum run length will be between 32 and 64. Let us say we are choosing 32, which means whenever we are choosing a run, it should at least be of size 32. So if you are already getting naturally occurring run, which is more than 32 in size, well and good. If you are not getting naturally occurring run, what will you do? Let us say you got a naturally occurring run of 10 elements and the remaining are not sorted. Maybe the largest piece in this run is of 10 elements. There may be another piece of, let us say, 3 elements which are also sorted. When you get these sort of data, you will use insertion sort and make it match with the minimum run length. What if you get something larger than minimum run length? Let us say you got a run of 45 elements which is already sorted. So you will take this as the run. But in case you are getting some value lesser than the minimum run length, then you will use insertion sort in order to make sure that that particular run is completely sorted. So this is the only point where insertion sort is used in tim sort. Okay. So let us assume that all these separate runs are sorted by this point. So let us say 1, 2, 3, 4. These are your 4 runs in this particular data set which are already in ascending order. Okay. Because you applied insertion sort in case it is already not in order. What is the next step? Next step is to merge your runs. So while merging, there is a particular process to be followed. The process is you should always have a stack in order to do your merging. What is the need of the stack? The need is that when you are inserting runs into the stack, so okay, initially, whenever you have a stack, as soon as you identify, whenever you have a run, that is, as soon as you identify a run, you have to put that run into a stack. This is rule number 1. So you got these runs, 1, 2, 3, 4, A, B, C, D, anything is fine. So I'll use 1, 2, 3, 4 itself here. So in this, okay, I may have numbers to be used. So I'll put A, B, C, D itself. So let us say A, B, C, D are the runs. What will I do? Once I have these runs, once A is identified, I'll add run A to the stack. Similarly, once run B is identified, as soon as the run is identified, I'll put that run into the stack. What about run C? Again, as soon as run C is identified, I'll put it into stack. So this is how I'll keep adding all the runs onto the stack. Finally, I have to merge all these runs. But there is one more trick that we are doing. That is, when you are inserting it into the stack, you are not simply inserting. Instead, you have to check 2 conditions. If either of those conditions are violated, you have to perform a merging then and there without waiting for completion of the stack. I'll show you when this is to be done. Let us assume that you already have a lot of data in the stack and we are only concerned about the top 3 elements of the stack, that is top 3 runs. So let us say A, B, C are the top 3 runs. Okay. So A is on the topmost position. Then you have B and C, which means I have newly inserted A. A is the most freshly inserted run. So while inserting A, just after I insert, I have to check 2 conditions. And if either of these conditions are violated, I have to do a merging then and there at this point. Okay. So the 2 conditions are, first condition says C should always be greater than B plus A. That is, your lowermost run that is among the top 3. Among the top 3, the lowermost run should be having a size which is greater than the sum of those of top two. This is the first condition. Second condition says B should always be greater than A. So when I say A, B, etc., I mean length of those runs. Okay. So length of B should be greater than length of A. That is one condition. Length of C should be greater than the sum of lengths of A and B. So these two conditions, if either of these conditions are violated, what we'll do is we'll merge run B with whichever is smaller among A and C. So B is constant. You have to merge B because either you merge with A or with C, B is the one you can merge with. You can only merge two closer stacks. Okay. You can't merge A and C. So if you want to merge any of these, B is the common part. Among A and C, whichever is the smaller run, that is what you are going to use for merging. This is the rule. So whenever you are adding a run, you'll make sure this rule is satisfied. If not, you have to do merging then and there. And then you have to recursively check it with the previous one in case it is violated. If it is not violated, well and good, you can stop there. Okay. So this is how you insert each into the stack. Let us say you inserted all elements. Finally, whatever you are having, you have to do a merging on all those in the stack once you are completed with adding all the runs. While doing that, again you have to check for these two conditions at each step. So this is the rule for team sort. Let us do one thing. We'll take some numbers and try to identify this. Keep these two rules in your mind. Okay, I will not erase those rules. Let those stay there. Let my numbers be 42, 70, 12, 30, 24, 42 again, 88, 51, 33, and let us say 40. So these are my different elements. So I'm choosing my minimum run length as 4. So just for keeping it simple, I'm choosing 4. So each set of 4 elements as of now I'm considering to be my runs. So considering my first set of 4 elements, what will I do? Initially, I'll try to identify naturally occurring runs. So I'll initially identify that there are 2 elements which are part of naturally occurring run. But this does not satisfy the minimum run property. What will I do? I'll try to extend it by having 2 more elements so that my minimum run condition is satisfied. So 4 other. What about the next? Again, I can find 42 and 88 are following, but there is no other element following. So I'll add these. Okay, 24, 42, 88. 3 elements are following here. See, there is a naturally occurring run of 3 elements, but again it is lesser than my minimum length. So what will I do? I'll add 51 as well. So I'll have 4 elements again in second run. Only 2 are remaining. So these will be my part of third run. What happens now? I'll sort this first run using insertion sort. What happens? 12 and 30 are smaller. So elements will be 12, 30, 42 and 70. This will be my run 1. Okay, this is my run 1. So I'll insert run 1 into the stack. 1 is inserted. What about run 2? So run 2, these are the 4 elements. You know 24, 42 and 88. They are all in order. 51 is to be inserted. So my run 2 will have 24, 42, 51 and 88. That is after insertion sort. This is my run 2. Run 2 is also the still I don't have 3 in the stack. So I can continue. My third run is having 33 and 40 and it is already sorted. So my third run is here. What am I going to do? I am going to check these conditions. And how should I check? A, B and C should be from top to bottom. A should be on the top. I have to first check B greater than A. Is that condition satisfied? B is, what is the size of B? It is 4. What is the size of A? It is 2. Only 2 elements are there in A, which means B greater than A is satisfied. My second condition is satisfied. What about the first condition? C greater than B plus A. C, what is the size of C? 4. What is the size of B? It is also 4. What is the size of A? It is 2. So C, is it greater than B plus A? B plus A is 2 plus 4, which is 6. What about C? C is 4. So the first condition, which was C greater than B plus A, this is violated. So whenever condition is violated, what should you do? You should merge whatever is in the middle, that is B, with smaller among A and C. So which is smaller here? A is smaller, which means you have to merge B with A. So how will you merge B with A? This is my B. If I merge with A, 33 and 40, after 24, I'll have 33 and 40. So I'm going to add here 24, 33, 40, then 42 and so on. So what I did, I modified my run. So I merged these two. This will become single entry, A, B, I'll call them. So now I only have two elements. One is two runs, one is this, one is this. If I merge them, I'll get final sorted order. So I'm going to merge this and this. That is it. So you understood the process, right? If I merge, I'll get the final sorted order. Next step is, let us run the identify the pseudocode. We'll write the pseudocode for team sort, and then let us see if it is clear for you. So next step is writing the pseudocode. So while writing the pseudocode, what should you keep in mind? You should know that first step is to identify your min run, the length of min run. Then you should have a stack. Into that stack, you should keep adding runs one by one. While you are adding, you should check for the condition and merge if required. Once all these adding to the stack steps are completed, you can merge all the remaining runs. So again, even during this point, you have to check the conditions. Okay. So these are the steps to be done. Let us write the pseudocode for this. So in the pseudocode, what should you have? Let us say tim sort input will be an array. Let us say an array. First thing, you have to identify the min run length. So length of min run, I'll call it as min run. It should be just the length. Okay. Min run, it's an underscore here. Okay. Min run is equal to, I'll just write the name of a function. Let us say determine min run. So this function I'm not going to elaborate. As of now, you can just assume that this function will give you one value. That value is taken to be the minimum run length that you should follow. This is based on the length of array. So length of array. Based on your length of your array, you will have a value of minimum run length that is to be taken. Next thing, you should have an empty stack. So let us say runs. Runs is the stack you are having. This is an empty stack. Okay. Once you have the empty stack, what should you do? You should go through each of the runs that you're finding, which is at least of the size of this minimum run. And while you're going through all the runs, you have to keep inserting runs onto the stack. So for each run, let us say in, I'll again write a function which is supposed to find the runs. Okay. The reason I'm not elaborating this is it's not as straightforward as you would think, because it's something that is used in many of the languages, and you just need an overall idea of what is going on. That is why I gave you the overall idea of what is going on. Exact is a bit difficult to find out because it's not straightforward, and I don't want to go into the complete details in this lecture. Okay, so find runs inside this array, and you should know what is the min run as well, because minimum this much should be the size of run. So let us assume that this will provide you each run one by one. So from here, each run you'll be able to find by the name run. Once you get the run, what should you do? You have to sort that run. That is the next step. So sort, how will you sort? You'll use insertion sort. Let us say insertion sort on run, each of the run that you got. So you got one run, on that you ran insertion sort. After doing insertion sort, what should you do? you have to push this run onto the stack. So your stack is runs, let us say runs dot push of run, right? So you are pushing the run onto the stack named as runs. What is the next thing? You have to do the merge procedure in the stack, the conditional merge that we talked about. So let us call it as merge stack, merge stack of runs. So runs is the name of the stack that, okay, this run is capital that we used. So I'll use capital itself. So what are we doing here? We are going to runs. So in this step, we are going to use the two conditions that we discussed, and according to the condition, we'll do the merging. Okay. So once you come out of this for loop, what happens is you have completed inserting all the runs onto the stack, and while inserting whatever conditions are to be checked, you checked all of those already. What is the next step? You already have the final set of runs in the stack. You have to merge all of those. So how are you going to do? Let us say while, it's a while loop till the stack is empty, or let us say length of runs is greater than 1, which means if there is something in the stack. Okay, what should you do? You should keep merging. So okay, so here you should keep merging them. Let us say merge. So here you're going to merge the top ones in case there are no violations. Okay. So if there are violations, you have to use whatever conditions we already discussed. If there are no violations of the conditions, you will merge top two runs. This is what you're going to do. Once you are done with this, you are done with all, you finally have the final array, you can return whatever is the merged array. Okay. So this is the algorithm required for Tim sort. So this is the, let us just go once through the process that we followed. First step is you have to identify the minimum run. Next step is you have to create an empty stack. Then while you are going through each of the runs, you have to identify the runs. How do you identify? One is identify naturally occurring runs. Second, if there is any run which is in reverse order, you just reverse it and make it a run. Otherwise, use insertion sort to make it of at least minimum length. Okay. So once you find this run, what is to be done? Do insertion sort to make it at least minimum length. Then you have to push it to the stack. Then you have to follow merge procedure, right? Under three conditions that we discussed. After this, you have to, once complete all the runs are added to the stack, you have to merge all the remaining runs. Again, this time, even if conditions are not violated, you have to merge top two runs in the stack. But if conditions are violated, then you have to check for the conditions and do the merge process. Okay. So this is the algorithm to be followed. One more thing, what about the time complexity, space complexity and all? First thing, in best case, you can have an order of n time complexity, but generally we are not concerned about best case. That is not we are looking into. We are mostly concerned about worst case and sometimes average case. So in case of Tim sort, both the worst case as well as average case is order of n log n. But the speciality of Tim sort, as we already discussed, is that under real world scenarios, whenever you have an actual real world data set, Tim sort always outperforms other sorting algorithms like quicksort and all. This is why it is used in multiple libraries. So Tim sort has an order of n log n time complexity. And is it stable and in place? No, it is not in place, but it is stable. Okay, stable because we are using merge sort and insert, insertion sort, both are stable. So automatically Tim sort is also stable. So it is stable but not in place. Why is it not in place? Because we are using merge sort, and merge sort is not going to be in place. And then what will be the space complexity? Order of n. So this is same as what merge sort does. It is taking extra space in order to do merging. So time complexity is order of n log n, space complexity order of n, Then is it stable? Yes, it is stable. And is it in place? No, it is not.